Some discussion about new topics from Chapter 3 about atoms and ionic bonds. And we have an interesting picture of a statue carved out of salt in a salt mine in Poland. Interesting in that picture from your textbook. Well, where are we going with this chapter? Wow, look at the learning objectives. I don't want you to be scared off by them right now, but realize we're going to cover each of these sooner or later, and we're going to start with this first recording here talking about substances that are ionic versus molecular, and we're going to go on later to talk about formulas for these things later. So, starting with simpler topics. Ions, molecules, and chemical bonds. What are ions and molecules, and how are they different, and what holds them together? Well, a covalent bond is what you get when two atoms are sharing pairs of electrons. Typically, we're going to have nonmetals and other nonmetals and sharing those electrons in what we call a covalent bond, making a molecule. It's like picturing this tug-of-war event where there's opposite forces pulling on the same thing. Same idea applies when we're looking at atoms together between two nuclei. Both the nuclei are positive, and they're going to pull on those negatively charged electrons and holding them together in what we call a covalent bond. It's another representation for this is kind of a cartoony fashion, but electronic sharing of electrons between two atoms, a pair of shared electrons, is called a covalent bond. And let me write that in here. One pair of shared electrons is a covalent bond. And so if you're sharing electrons between atoms, that's what we call making a molecule. It's a very stable thing, holds them together between nonmetals typically. So we will represent these molecules in different ways. Sometimes they're going to be simpler than others, and you get used to them gradually. Notice these are all models in one way or the other, and some models are more convenient, some are more confusing. Realize that they're all representations to give us an idea how things are connected. The top row shows what we call ball and stick models. They look like little sticks on balls and joined together. The sticks, therefore, would be the connectors, namely the bonds, and the little round spheres representing the atoms. Remembering that atoms have various radii, but they tend to look kind of all the same in ball and stick models. They don't tend to have different radii when we use those models. The space-filling models are the bottom row, and they portray the overall shape of molecules, but they don't particularly show the bonds explicitly because they're kind of buried in that space, the non-existent space, so there's space-filling between the two atoms. So two different representations of each of those compounds here, the first one being hydrogen chloride, HCl. The second one is water. The third one, ammonia, and the last one is methane. There is some things to notice about these things. Chlorine is commonly shown in green. Oxygen is commonly shown red. Unless you have color issues, these will be fine for you. Nitrogen is commonly blue, and carbon is commonly black. So when we're using these types of representations, those will become familiar to you gradually. Obviously, then the other atom that's in these representations must be the hydrogen. So it's listed in your descriptions as either ivory or gray or white, whatever you want to think of them to be. They're kind of gray in this image, I guess. Now, other ways of representing molecules in different models are represented here. This compound is called ethanol or ethyl alcohol. You don't have to know it by name at the moment. And ethanol, you've probably heard of that in common encounters, can be shown as this chemical formula on the left, which tells you precisely how many atoms and which kinds. The structural formula in the center shows you the atoms and where they connect to one another, but only using letters and lines to represent the bonds. The molecular model on the right is like the ball and stick representation on the previous slide. So each of those represents the same thing in different ways. All models are wrong in general, but mostly they're helpful. So we have to recognize there's sometimes limitations in what the models will show. Now, there's a bunch of molecules that occur naturally that you need to think about and be aware of and know them. They're diatomic because there's always two. So something occurs twice in that compound. And there are only certain elements, but you need to be aware of them because we'll describe chemical reactions later. We'll need to know that when somebody's talking about hydrogen in a reaction, it's always going to be H2, unless someone specifies differently. The typical, normally, naturally occurring forms for these few elements is always diatomic. And so hydrogen, nitrogen, oxygen, and fluorine and all the halogens below it, are always going to occur in diatomic form. So it doesn't matter what the reaction is, we're going to expect to see these always in pairs. So you need to be familiar with them. Recognize that it's kind of a 7, if you will, or an upside down L on the right. In other words, that group 7 elements plus hydrogen, nitrogen, and oxygen. Hydrogen, nitrogen, and oxygen happen to be gases. So is fluorine and chlorine. Bromine is a liquid, interestingly, and iodine is a solid. Interesting little tidbits. Hydrogen, nitrogen, and oxygen as gases. Maybe you've heard of nitrogen and oxygen, but yes, hydrogen is also a gas. Good things to think about and to be aware of when we're talking about various kinds of covalent molecules. These are some of the simple ones. We will get into more detail later to explain why they occur as diatomic molecules to make sense of that. Okay, so when we go beyond the molecules with covalent bonds, we're going to go to compounds that have ionic bonds. The ionic bonds are when you have opposite charges attracting. Opposites attract, right? You've heard of that somewhere. And we call that electrostatic attraction between charged particles. So one is going to be plus and another one's going to be minus. And it results when electrons are transferred from one atom to another. Generally speaking, these will commonly be a metal with a non-metal. So the charged particles are what we call ions. And an ion means that you have the number of protons is not the same as the number of electrons. In other words, you get more plus or more minus depending upon whether there's more protons or electrons in a particular ion. So there's two types of ions apparently, and they're called cations. Think of the animal, don't say cation, that sounds silly because it's not the way we use it. Cations and anions. The cation is the positively charged particle, and I first learned it this way, see if it works for you. Its symbol is in the middle of its name. It's a positively charged particle. Metals are going to be the elements that tend to lose electrons and become cations. We'll talk about them more gradually, don't panic. The anions are going to be negatively charged, and you just have to get used to the fact that anions are negative and cations are positive. The nonmetals will be the opposite then. So if we're going to use a metal and a nonmetal, the metal is typically positively charged ion, the nonmetal is the negatively charged ion, combining to form what we call ionic bonds, ionic compounds. And we'll try to remember these things in various ways. It takes practice. You'll get used to them. And one way to think of it is cations are positive. For you that are cat fans, maybe that works for you. Okay, so talk about cations a little bit more. How do we get a positively charged ion? Well, you have to lose an electron so that the number of electrons is less than the number of protons. So cations, more protons than electrons will be present. And let's think of an example of how that would work. So here's a sodium atom. We've talked about sodium and its electron configuration. It's shown in a stacked formation here on the left with 1s2 at the bottom because it's closest to the nucleus, 3s1 at the top because it's farthest from the nucleus. In sodium, ordinary sodium is going to have 11 protons no matter what. And in a sodium atom, it will also have the same number of electrons, same numbers, right? Because it's just the atom. Well, what happens then if you lose an electron? So if you lose an electron, which one is most likely to be lost? The one that's farthest from the positive charges will be the least tightly held, and so the electron that will be lost will be the outer shell electron. Outer shell electrons are going to be where things will change. And so if you lose an electron, now you're down to the sodium ion that has 10 electrons and 11 protons. So 11 protons, 10 electrons. The charge is going to be 1 plus 1. One more plus than than the electrons. That's how you get the plus charge on the sodium ion. And that makes some kind of sense if you think about it. The point also, though, is to notice that when you lose that outer electron from the sodium atom, you end up with a full outer shell, the second shell in this case, on the sodium ion. There's something very stable about that. We're going to continue that discussion as we go. The other type of ion, then the anion, has to have more negative charge, so more electrons than protons. That's what the negative charge results from. And the nonmetals are going to go that direction. Typically, things such as group 7A elements, including chlorine, will have a negative charge because they gain electrons. They've got to gain them from someplace to get an extra negative charge. Well, think about this example with chlorine. The chlorine atom is element number 17, so the number of protons equals the number of electrons. The electron configuration shown similar to the one on the previous example with sodium. First shell lower than second shell, and the third shell on top, the farthest from the nucleus. So in this case, the nonmetal chlorine will gain an electron, and it will go into the only available place, namely its outer shell, to add one more from 7 to 8. And now it has 17 protons and 18 electrons for the overall charge now to be more negative than positive. And the negative charge of 1 is what is represented with this symbol here. 17 protons, 18 electrons, 1 extra negative charge, a negative charge on the ion is represented with a superscript. Do not think that that negative sign here means that you have lost anything. It means that you have an extra electron. It's very tempting to think otherwise. So where does it gain that extra electron? In the outer shell. And again, we result in something that has a full outer shell for chlorine. They call it a chlorine ion. More specifically, it's going to be called chloride. That might not sound too surprising to you. You might have heard of chloride in sodium chloride. So here's our example that makes it a cartoon. Had to get rid of the extra line for you. So if one atom is talking to the other, I lost an electron. Are you positive? Of course you are, because if you lose an electron, you have more positive than negative charges. Silliness that we like to share because we like silly chemistry jokes. Okay, and here's the next one from Frank and Ernest, and go figure, we've been using this example for quite some time. You've lost an electron. Are you sure you're all right? One atom says to the other, I'm positive. So if you lose a negative charge, you end up with a positive. Cute. Okay, keeps you laughing. Now, talk some more about ions, molecules, and chemical bonds. So where do these things come from? We've described how sodium could lose an electron, chlorine could gain an electron, becoming ions. Chlorine is over there on the left. It's a toxic green gas. It is going to be as the formula Cl2 in that container. It's described as a glass ampule. And that solid sodium is the metal down there at the bottom of the diagram. And these things too can combine, these two items, chemicals can combine if with the right conditions to make what we know as sodium chloride. Our friend table salt, well, it might be your friend as long as you like it. And so each of these things are very unique in their properties. Sodium chloride, being a solid, is very harmless. Sodium is a very reactive metal. If you were in class, you may have seen me react sodium in water. And chlorine is a toxic, nasty gas. You wouldn't want to breathe it. And it's sometimes used in chlorinating swimming pools. So how does the chlorine react with the sodium to make sodium chloride? What's going to happen in that formation of sodium chloride? An electron is seriously and literally transferred from the sodium atom to a chlorine atom. Looking back at the diagrams I showed you a minute ago, the sodium atom was going to lose an electron and turn into a sodium ion, losing an electron. And where's that electron going to go? Well, apparently chlorine is going to gain that electron and turn into a chlorine ion, whose name is more correctly chloride. I wanted to know that name here because calling it a chlorine ion sounds a little funny. We call it chloride. So if the sodium has to lose one and the chlorine has to gain one, then you end up with opposite charges that will attract opposite ions, a cation and an anion that combine to make the ionic compound. Another way of looking at it is when looking at the tallies of protons and electrons. Sodium with 11 protons and 11 electrons, chlorine, Cl2, but one atom has 17 protons and 17 electrons. When you combine them to make the sodium chloride, you have sodium ions and chloride ions. The total number of protons hasn't changed, but the location of the electrons has shifted. So one of them has been acquired by chloride, and it's literally transferring from the sodium to a chlorine and making this ionic bond. So they're connected by attraction of opposite charges in what we call the ionic bond. So the transfer of electrons is key when we're talking about ionic compounds and ionic bonds. Another example of an ionic bond forming in another representation that might be valuable to you is a lithium compound, lithium reacting with bromine. Lithium, as you might recall, is element number 3. And all that's shown here is valence electrons. So lithium has an electron configuration of what? Well, it's got 3 electrons. So it's 1s2, 2s1. And so that is its valence electron right here. And its valence electron is what is going to be donated, transferred from the lithium atom to the bromine atom. The bromine has an electron configuration with a lot more parts, so let's not do it the hard way, but let's remember just the valence electrons. And the valence electrons of bromine are going to be which? Well, they'll be, bromine is in the 4th period, so it's going to be 4s2, 4p5. And so if it takes these total of 7 valence electrons, because it's in group 7, remember that, it's going to pick up one more, and now after lithium has donated an electron to the bromine, now we have a lithium ion and a bromide ion, and there should be 1, 2, 3, 4, 5, 6, whoops, the tool needs to write, 6, 7, 8 electrons, where we already previously only had 1, 2, 3, 4, 5, 6, and 7. So you've gained an electron, and we're going to be outer shell electrons. It will fill up the outer shell for the bromide ion when it has transferred from the lithium. The compound that results is going to be called lithium bromide. We'll talk about names and formulas gradually. So again, this is an example of where the electron is literally transferred from one to the other as cations and anions are formed. So here comes another one. The way we think about ionic compounds may be relatable to you if you're a James Bond fan. Mr. Bond liked to say that he wanted his martinis shaken, not stirred. If you're a Bond fan, you've heard this. Well, if you don't have to know Bond to think about it another way, ionic bond is a bond where the electrons are taken, not shared. So shared electrons are for covalent molecules. Covalent molecules. And taken, when the electrons are taken, that would be for the ionic compounds. So if we want to remember which one is which, the ionic bond has electrons that are taken, not shared. One other way of looking at an ionic compound with the formation of sodium and chlorine into sodium chloride uses these spherical representations for different ions. You can tell they have different sizes in this particular diagram. The chlorine, as I'd mentioned earlier, is green, and the sodium ions, or sodium atoms and ions, are purple. And so when they combine to make an ionic compound, the formation of this results in what we describe as a crystalline structure. Every sodium ion is surrounded on all sides by chloride ions. This one's because it's a cubical structure. And every chloride ion is surrounded on all 6 sides by sodium ions. So it's compact, packed together, so every sodium ion is completely surrounded by chloride. Every chloride is completely surrounded by sodium, except for if you're on the surfaces, of course. It results in these interesting and very elegant looking, or lovely, crystalline structures, as shown on the left. If you took a magnifying device to your salt shaker contents, you would see something like that. So ionic compounds are going to form into crystals when they occur, and this one happens to be a ratio of 1 sodium with 1 chloride. Not all ionic compounds are going to be that way. Just one example. And so if you have an element who's lost an electron, that poor electron is out of its element. Silly jokes, I know. We have to put in some humor when it's available. Okay, so let's do one more thing before we conclude this discussion. This is an example that gives us a way to think about how the representations of these compounds are going to be viewed. Which is likely to represent ionic compound and which is going to be a molecular or covalent, same idea, compound, and why? What are the characteristics of each? Well, there are 2 different atoms combining in each example, and we have to decide whether a repeating set of blue spheres and yellow spheres in rows represents one versus the one where you just have pairs of little spheres in little combinations. And so hopefully the diagram on the previous slide with the sodium chloride gets you the idea that the ionic compound should be the one that has a regular crystalline array, and the covalent compound is going to be the example number 2, where there are individual pairs of atoms combining. Now, we're not saying what the blue and the yellow represent here. It isn't really important to the example, but the ionic compound will be the one where you have a regular pattern of closely packed spheres. In this case, they'd represent the ions, and the molecular compound is the other way. So once again, if you can recall what I just said about ionic compounds, in the ionic bond, the electrons are taken, not shared, and they sit together, closely packed in spherical arrangements. If you look at this diagram closely, it is actually sodium purple and green chloride in that martini glass. That will be enough for this section. It's a long enough recording. I hope you find this helpful as you proceed with your homework. You can look for more information on the next section of the chapter in the next recording.